Alright, ATSEVS533 students, welcome back. We're now on our second day of lecture about Chapter 1 in the IPCC report, Assessment Report 5. And I just wanted to kind of go over a little bit about just how bad the situation is in some ways in the climate, with regard to climate change real quick. Now, I am recording this in late December of 2016, so that I'm ahead of you a little bit here, and I might reuse this lecture once. So I apologize that this information is a little out of date. Now, every year in January, you start seeing these horror stories where like NOAA and NASA start announcing that the previous year was the hottest year on record, or second hottest year on record, or something like that. This is just one from at the end of last year, since those kind of announcements haven't come out yet. But like 2015 was easily the hottest year on record. In fact, to have a quote from that particular article there, 2015 was the hottest year on record according to new data released Wednesday by NOAA and NASA. NOAA is the National Oceanographic and Atmospheric Administration. For the last 12 months, the average surface temperature across the globe was 58, a 2.3 degree Fahrenheit increase over 2014's record-breaking average temperature. The two agencies reported that is a 1.24 degrees above the 20th century average, which of course was already a warm period. Earth's temperature has increased by 1.8 degrees Fahrenheit since the late 19th century. That's just crazy. In fact, when you take a look at a graph that shows temperature anomalies globally since the 1880s, you can just see not only are we in this very unfortunate trend, but look how much bigger the bar is for 2015 than 2014, and 2014 was already horrible. I mean, this is just no good at all. And undoubtedly, when you're watching this, you've just recently been seeing stories on the news about how 2016 was the warmest year on record, and if I reuse this lecture next year, it'll be 2017 was the warmest on record. That's all really stressful. Alright, just to review before we move forward here from last time, we talked about the structure, the nature anyway, of the Intergovernmental Panel on Climate Change. Remember, it is somewhere in the neighborhood of a few hundred scientists working in different committees that, their working groups and subgroups and so on. The whole organization was set up by the United Nations Environment Program and the World Meteorological Organization as a way of informing governments about the state of the art and our knowledge of climate and climate change. We had to actually spend some time talking about a definition of weather and climate. That's kind of always a necessary thing when you're talking about climate science. And we learned that there was more to this notion of climate than just the average. Although average is important, we typically have to talk about like a 30-year average of the temperature at a location. There's good statistical reasons why it needs to be 30 years. But it can also be about like changes in the variability of the weather. Maybe there is a larger difference between coldest and warmest days. Maybe there's a smaller difference between coldest and warmest days. Maybe there's more variance, maybe there's less variance, and maybe there's trends and so on going on. Remember, we also talked about the fact that we're going to have to figure out how to partition natural climate changes and natural climate variability from the so-called anthropogenic sources of climate variability. But no matter what, we use the term climate change to describe both, okay? Whether the climate change was caused by the addition of greenhouse gases in the atmosphere, or whether it is due to volcanism or a comet impact, or changes in the Earth's orbit, or internal variability of the climate system, and so on. We talked about the fact that one of the very strongest ways that one of the strongest pieces of evidence that we have about climate change is that multiple independent sources of information are all in agreement. That is, in fact, if you think about theory and philosophy of science and so on, that's in fact one of the very strongest things we can hope for when we are studying a phenomenon, is that independent sources of information are in agreement. And there's no doubt about it. Whether you're talking about satellite data or in-situ observations from weather stations, or whether you're talking about buoys or models or theory, it's all in agreement. And not just in agreement like it all says the planet should be getting warmer, they're all in agreement about how much the planet should be getting warmer. It would be strange if theory was telling us that based on the amount of greenhouse gases we've added to the atmosphere, the planet should be 100 degrees Fahrenheit warmer than it is. That would be a strong piece of evidence that something is wrong. But they all are in agreement that the planet should be have increased in its temperature by about 1.5 Fahrenheit, something like that. And that's about what it has happened. Let's see here. Last time we also talked about these climate change indicators. We talked kind of just as a survey of them to know what we're going to be looking for in the cryosphere, in the hydrosphere, at land surface processes, atmospheric processes, and so on. We talked about this idea of temperature anomalies and how you compute an anomaly based on an average at a location. So like this map here of temperature anomalies shows us that Central Africa was warmer than Central Africa usually is, and showed us that, let's just say, Greenland was colder than Greenland normally is in June of 2009. Okay? They are defined at a location. And so we talked about the value, too, of this business of using anomalies, and how, like, on this map of Colorado, we could see how at different locations, based on different altitudes and so on, we had radically different temperatures, but they could, in fact, all have very similar temperature anomalies. They could all be a degree or two above normal, or they could all be a degree or two below normal right now. It's just hard to tell when you look at the absolute values of the temperature at each of these locations. So what I want to do at the beginning of the lecture today is actually start talking about what is the source of the problem from an anthropogenic point of view, okay? We will, at a later date, talk about natural climate variability due to changes in the Earth's orbit and so on, which is a really interesting topic that often students don't really have a good handle on. But obviously, in a class about environmental issues associated with climate change and so on, what we're really talking about is the addition of all these greenhouse gases to the atmosphere. And I'm going to be stealing a couple of graphs here that come from the EPA's website. And the main greenhouse gases that this reference is concerning itself with, remember greenhouse gases, that is to say the gases that are responsible for the greenhouse effect, the greenhouse gases that we are emitting, notice that the graph is labeled greenhouse gas emissions, are carbon dioxide, methane, nitrous oxides, and various fluorinated gases. That's going to be things like freon and so on. This is not the same as saying what's the most important greenhouse gases or whatever. I mean, for example, you'll notice water vapor is not on here. Water vapor is an important part of the greenhouse effect, although it's a feedback, not a forcing. We'll learn about that detail later. Ozone isn't on here. Now that gets a little bit complicated. Don't confuse the ozone hole, which is another environmental issue, with the fact that ozone also happens to be a greenhouse gas. But we don't emit lots of ozone, so this is because this is an inventory of our emissions. It isn't on that list. And of course you see, oh my goodness, if you look at the inventory of what we are emitting, we emit enormous amounts of carbon dioxide, and that's why carbon dioxide in concentrations are increasing. This is just an annually averaged global values of carbon dioxide tracing back to the 1950s, which is about when we started routinely measuring carbon dioxide at certain sites around the world. So these are annually averaged. Later when we learn more about the carbon cycle, you'll see that there's actually variability within the year as well. But annually averaged, you get this nice smooth curve, and you can see that it's increasing dramatically. I want to draw your attention to the fact that the units of the amount of carbon dioxide in the Earth's atmosphere is in terms of parts per million. Carbon dioxide concentrations are relatively small. It is a trace gas in the Earth's atmosphere, but it's obviously a radiatively very important gas. It has an important role in maintaining the temperature of the Earth. Notice that the graph that they show you here does not start at 0 on the y-axis. In 1950, we were observing values around 310 parts per million of carbon dioxide in the Earth's atmosphere. Pre-industrial values, just to give you a sense, were around 280 parts per million. Later we'll learn how we know that and so on, but a good pre-industrial value before we started discovering all the useful things you can do with fossil fuels and so on was about 280 parts per million. And currently we're sitting at around 400, a little bit more than 400 parts per million. And you can see how this graph moves forward with various projections as to how much carbon dioxide will be in the atmosphere in the future. Each of those projections is based on certain assumptions. There's different scenarios that the IPCC works with as to, like, different assumptions about how the economy is going to work and the transition to green sources of energy and so on. But you can see that all of those projections involve the amount of carbon dioxide in the Earth's atmosphere increasing. We, even under the most optimistic scenarios, don't get off fossil fuels enough in the coming decades for carbon dioxide to start going down. In fact, as we're going to be learning, it's going to take centuries to millennia before we start actually decreasing the amount of carbon dioxide in the Earth's atmosphere. We will obviously be spending a lot of time this semester about the role of carbon dioxide in the Earth's atmosphere. If we wanted to look about where it's all coming from in terms of United States emissions of carbon dioxide, the single largest source at the present time is generation of electricity. We produce most of our electricity in the United States from non-renewable sources of energy like coal or natural gas. There are a few others. There's some energy that's produced from petroleum and so on. But we generally don't produce our electricity. Some is now from nuclear, obviously. Some is solar, some is wind. But unfortunately, still an enormous amount of electricity. It comes from non-renewable sources of fossil fuels. Obviously, transportation is another important source of emissions of carbon dioxide into the Earth's atmosphere. We don't really have the infrastructure yet to have large fleets of electrical cars and so on. Industry itself directly, like as in smelting of aluminum and so on, produces an enormous amount of carbon dioxide as well. There's also, for example, the residential and commercial usage directly for things like heat and so on. Boy, what I'm noticing about these things is they're all stuff we really need. Okay? It's going to be really hard to figure out how to fix that problem of transportation needing carbon dioxide, resulting in a lot of carbon dioxide emissions. Because cars are plentiful. There's hundreds of millions of them in the United States, and they are cheap, and they use fuel, which is cheap. How are we going to get off of that? Electricity? Good grief, just here in this room I'm in, I've got 5 computers running, plus the lights for the filming, plus tablets, plus the timer that I use down here to make sure I don't run too long, plus cameras. I'm using a ton of electricity just in this room. How are we going to get off of that? How are we going to switch to things like solar and so on? Oh, let's talk about some sources of greenhouse gases you might be less familiar with, like methane. This again is our track of methane over the last 60 years or something like that, and then various projections forward under different scenarios. Again, the IPCC makes these graphs based on different sets of assumptions about, well, what if the economy did this? What if we switched to this? What if they're, etc. We'll learn about how these scenarios work in a future lecture. But you can see in all of them, methane continues to increase. And methane is a very effective greenhouse gas. It is about 20 times more effective per molecule than carbon dioxide. Now, if you actually look at the dotted line there, you'll notice here, well, first off, notice that the graph is in parts per billion. Methane is a much less common gas in the Earth's atmosphere than carbon dioxide is, much less abundant. And what I want you to notice is that methane concentrations, CH4 concentrations, actually have been fairly flat for the last 10 years or so. There's a lot of reasons for that. We actually were pretty good at getting rid of some of the easy sources. There were various ways methane was getting into the atmosphere that were not hard to fix, things like landfills and so on. What we are proving to be less good at is the sources of methane that are associated with leaks in the natural gas delivery system, and as with the increase in fracking and so on, where there's more natural gas delivery, this is a problem that is growing faster than what we're fixing. So, unfortunately, that leveling off of methane concentrations in the Earth's atmosphere is not going to last. But at least it's not getting worse at the present time. That's a good thing. Because it's less familiar to most people that methane is a greenhouse gas, let me see here. Methane is actually about 10% of all of the greenhouse gas emissions that come from human activities. We're going to see something about the sources about it a little bit, but it turns out at the present time, natural gas delivery systems, methane is natural gas, like what you burn in your stove, or if you have gas heat in your house, or a gas hot water heater. And it turns out the system that delivers that is really leaky, both in terms of how we extract natural gas from the ground and how we deliver it. It turns out per cubic foot, natural gas has very little value, so the natural gas delivery companies have very little incentive to go and hunt down leaks in the system. Okay, so unfortunately a very large amount of the natural gas that we extract from the ground never gets used for anything. It just ends up in the atmosphere. Livestock is another important source of methane in the atmosphere. It's part of their natural digestive processes. That's just a nice way of saying cow farts. Okay, the digestive system of cattle produces enormous amounts of methane, and that is a greenhouse gas. Also, the processing of animal manure in lagoons. I don't know how much you know about animal husbandry in the modern world, but manure is often processed in kind of a little lake called a lagoon, and before it is able to be spread into the environment as a fertilizer or whatever, and that unfortunately produces a lot of methane as well. Let me go ahead and show you here. Here is from the EPA actual sources of methane emissions in the United States. And you can see the single largest chunk right now is the natural gas and petroleum systems, particularly the delivery systems. And because we're every year relying on natural gas more and more, which is not an entirely bad thing, but means that more and more gas is being delivered, more and more leaks in the system, and so on. And you can see enteric fermentation, that's a nice way of saying gas in the cattle's tummy and stuff like that, is another big sense. Landfills produce an enormous amount. Now we're getting better about harvesting the methane from landfills. We'll talk more about that later in the course. And then there are other processes that produce smaller amounts of methane and so on. How about nitrous oxide? Nitrous oxide is one that is people often don't know about. Nitrous oxide is laughing gas. If you've ever had the gas at the dentist office, it is that stuff. Nitrous oxide concentrations in the Earth's atmosphere are increasing dramatically. They are about 5% actually of all United States greenhouse gas emissions. The primary source of them is not dental offices. It is actually synthetic fertilizers. A number of different fertilizers, when applied to the ground, either break down into nitrous oxides or are nitrous oxides and so on. Certain transportation fuels actually emit out the tailpipe of jets and so on. There's a certain amount of nitrous oxides. But if you actually look at a graph from the EPA, it's clear agricultural processes are the main big problem for nitrous oxides in the Earth's atmosphere. Alright, let's take a few moments to answer a quick question about what we've seen so far. Question 1. According to the EPA, what is the single largest source of anthropogenic carbon dioxide emissions in the United States? Notice the key here is that it's carbon dioxide that we're talking about, and I guess for that matter that it's in the United States. Is it A, jet airline transportation, B, the burning of fossil fuels for electricity production, C, respiration in animals and bacteria, or D, photosynthesis in plants? Which is the single largest source of anthropogenic carbon dioxide? Make a choice in those 4 options and get a little feedback before you move on to the next question.